Now let's go. What did I intend to show? Okay, I promised to show something about concurrency and parallel programming. I won't show much because I only show you what's in the standard right now. And I also don't give you details. And if you don't know, let's say, what a log or a condition variable is, I could be able to explain that to you, but regarding the time frame, it will be too much to actually go into that detail. At least with C++ 11, we have in the language a definition what concurrent and parallel programming means. We have a so-called memory model in C++ now that specifies how the code that a C++ compiler generates should behave. And so the memory model is one of the important things, and it also, C++ 11 has some, even though it's controversial, simple feature to actually get into concurrent or parallel programming, and it's actually called a function called Async, which actually calls out another function where you can add parameters, and the option is that that other function is run in a separate thread, or whenever you need the result. And the principle behind that is actually you get, instead of the final result of calling the underlying function, you get a handle called a future, which is actually you can use later on to obtain the result of the computation of the function, of the underlying function. Or if the underlying function produces an error as an exception, the future object itself will also capture that exception and hand it to you. The async function, actually, the default might not employ any multi-threading. It might just put the actual call of the underlying function that you pass in as an argument on hold until you obtain the value from the future. And if you never try to get the value from the future, the function will never be called, which is maybe not what you intend to. But you can also force the execution in a separate thread by providing an additional argument to async, which is actually called a launch async, and that will spawn a new thread for executing the function, and whenever the function is done, you can actually get the result from the future. You don't have to explicitly synchronize with that other thread. The synchronization happens through the future object where you get the value from. And the
how efficient is this async implementation at the moment?
It heavily depends on your operating system and compiler. Today, it's not what you would like to run upstairs. It's something to, because spawning a thread can be quite an expensive operation. There is drive in the standard to get higher level abstractions for running things on GPUs, for example, and there are libraries already around there, but those are not standard C++ yet. Mauro, I'm sure, will know more details about those libraries. There's something called Thrust, for example. There are people who port parts of the standard algorithm library to perform in parallel mode, but the plain async is just for, let's say, for beginners and for simple coding, but even then, you might get a speed up from your, even on your multi-core on your laptop by having multiple threads employing the hardware that is available. Otherwise, you get a single-threaded program on a multi-core, and you get, let's say, if it's 4-core, you have a 25% utilization at max.
Yes, I mean, async is basically useful when you have a lot of work to do. So you can spawn a thread, and the time for spawning the thread is not big with respect to the actual computation you're doing. So it's kind of limited to coarse-grained parallelism. In that case, it actually works quite well. But if you have to do fine-grained stuff, it's not good. There are other libraries, and if you have time this afternoon, we'll go through it, which is called HPX. And they are also very active in the C++ standard committee to try to get something for the next standard release or the 2020 one.
At least what the advantage of async is, you can write parallel code today without thinking too much, because all the spawning of threads, synchronization, and so on happens under the hood. That's the highest level of abstraction you can get today. If you really want performance and you know what to do, you have to dig deeper and use the core facilities underneath, like managing thread pools and stuff like that. But that's not yet standardized, and there's also, it's kind of a political issue. There are different fractions who think their way is the best way, and they cannot agree on a single means to standardize, and that's why we don't have that yet. But at least we have the core basics to actually be able to specify that in a standard way today. Otherwise, before C++11, anything you got was you were at the discretion of your compiler and your thread library vendor, and if the compiler didn't comply with what the thread library would do, you just had bad luck. Sorry. One caution you should take, if you use lambdas, don't capture by reference, because if the lambda is run in a separate thread and you capture a variable by reference, that variable could be used by two or more threads concurrently, and if you don't protect that variable with the mutex, or if that isn't an atomic, then you will get the problem of data races. And if you have a data race, your program has undefined behavior, so you can get pink elephants raining from the ceiling or whatever, computers exploding, the water pipes spraying, or whatever happens from undefined behavior. I have a very brain dead and very bad, or that's a simple example. Let's say we have a function that does a very expensive calculation, which isn't what would be a square root, but if you have something that does some calculation and you have more things to do while the computation runs, you can actually start that function in a separate thread by using the launch policy of std launch async, calling async, and keep the result future object around, and later on, whenever you've done the remaining stuff, you can just obtain the result in the end. That's more or less how it works, and that's very simple to use and without getting too many headaches from running it. And it's not the best performance, but it's simple, and good performance and simplicity usually don't come that easy together. It takes a lot of work to get both of that. It's better than nothing, and it's better than creating a thread object, spawning a function there, and synchronizing on the result. That's more work to do, and it's already encapsulated here. I even tried to implement a very, very bad version of a Fibonacci number computation, just to show you that you can actually have use async to spawn off computations and then compute the results. It might start a thread. It will not in the default version, but I have another version where I actually spawn threads. The problem is that it might use too many resources. So if you ask it for a too large number to compute the Fibonacci number of that, you will get an exception because some resources might be used up. And I try to run that, and I get up to Fibonacci 15 or something like that. And if I try 20, it will just crash with an exception. And I haven't figured out which thing went wrong. Maybe too many threads started, or some other resource that was used up. But it's to show you that you can actually, if you can split a problem into sub-problems, you can spawn threads to sub-problems. But actually that is not a good example, because it's much easier and faster to compute Fibonacci numbers in a different way. It's just to show you as a simple example how to, let's say, apply sub-problems and spawn threads around that. I might be able to show you. So this is the version where I actually try to call async and in a synchronous way. And if I run that program, with 16, it runs for some time and terminates. Okay. Try to run it again. 15. I get 399 milliseconds, and if I use the non-asynchronous mode and run the same program, it's 4 milliseconds. Even that is a very brain-dead implementation, but it's starting threads and joining them is quite expensive if you don't do much in a thread. Just to show you, don't use it too eagerly. Do some real work in that separate thread, and then it could pay off to start it asynchronously.
Which, by the way, is a rule also for who writes OpenMP or writes everything. Just try to get the grain computation big enough until somebody from the sky give us some really fast runtime systems.
Even on the GPU, you want to do more work in a computation than just a simple addition.
The GPU is different. You might want to restructure a little bit, but you still don't have to think about the threads. It's not the single thread which is the unit of work. It's a CUDA block that you should consider as.
But even there, the barriers can be expensive, so you want to not do too many barriers.
Yes, obviously yes. You don't want to synchronize.
The future object itself that is returned by async is like a unique pointer, a unique thing. It should be called maybe unique future. So whenever it cannot be copied, you can only move it. So there's only a single handle to the future. On the other hand, there is a corresponding, like we have a unique pointer, a shared pointer, there's a thing called a shared future, and by calling the share member function on a non-shared future, you get a shared version of that future, and this one you can actually pass around, and you can have multiple places in your code where you actually get on the shared future, but this requires that the underlying result type is actually copyable if you want to use a shared future. With a regular future that is not shared, you can have a result type that is move only, even from calling the asynchronous function underneath. There's also one interesting thing is if you call get on a future or a shared future, calling that might actually require synchronization. So it might wait for the other thread to finish, or if it's not in an asynchronous mode, but in a default mode, it might actually compute the value when you call get. And this could be quite an overhead, especially if the computation takes some time. So that's, again, something to take into account. And that blocking of when calling get is a source of controversy within the standard committee as well of the future. And there are some specifications in the pipeline where we get more features around all this kind of future object and future handles to combine them, to have several things where you can say, is one of them ready or are all ready, so you can actually block on the availability of results that were computed in separate threads. There are low-level concurrency mechanisms in C++ that you could use, but I recommend if you're not an expert in concurrent programming, don't use them. But I tell you they exist. For example, you have a thread class. You have things like mutexes. Whenever you use a mutex to protect data, always use the wrapper lockguard, which implements the resource acquisition initialization. So whenever you want to hold on a lock, use a lockguard object, and when that lockguard object goes out of scope, it will automatically release the lock. This avoids that you keep the locks forever, and it will also help you to keep your locks only for a short period of time, as long as a block is where you actually created that lockguard object. Remember, if you create a lockguard object, you have to have a local variable. Otherwise, if you just create a temporary, it will acquire the lock and release it immediately, which is not a very good idea, usually. If you start a thread object, or if you create a thread object, the typical thing is you pass a piece of code, let's say either lambda or some other function, not returning anything, that is executed in that separate thread. And before you destroy a thread object, you have to join the thread, so it's always fork and join parallelism. Unless you say thread call the detach member function, which will run the thread as a kind of a daemon, and you have to do all synchronization with other means, for example, with the mutex or whatever, or condition variables to see where the other thread is working. And unless it's detached or joined, if you destroy a thread object, when the thread is still running, you will get a termination of the program, I believe. Yeah.
So obviously, multi-threading is the bread and butter of CSCS, so we can't live by your first rule. But a lot of our customers use OpenMP, for example. My question is, has there been any comparison of performance of different paradigms, for example, using futures? I know there's some people who've used futures in this room. Do we know anything about the relative performances of these paradigms? Maybe John would like to comment? I don't know.
I'm not an expert to actually, I know these things exist. I know the theory on how to apply them, but I don't have problems where I can actually apply them, where I'm really interested in the performance. So that's why I cannot answer your question. I know there are people who do these measurements, and maybe Mauro or some other people around here will be able to tell you more about that. But as of today, we don't have in the official standard of the C++ library, we don't have things that supports, let's say, GPUs that you have here. There is work ongoing, there are libraries ongoing, but these are not standardized yet. So anything that you compare, you cannot compare in principle, you can also only compare actual measurements with existing current versions of whatever library you're using. And you might have.
I would only add that under the hood, OpenMP is creating a thread pool effectively. It knows how many cores you've got, and it creates a thread per core, and then it schedules the work to run on those threads. And the actual code that you execute is never going to run faster on this architecture, or this thread scheduler, or that thread scheduler. It's only the sort of time between them and how you combine those threads which really makes a difference. So OpenMP and things like standard thread, if you had a thread pool, they should work out pretty much the same. If you weren't creating and destroying threads constantly, and if we have time to talk about HPX later, I'll mention that again.
Yes, I did few tests, and actually the stood threads are basically the same performance as a naive OpenMP. If you have a simple stuff and you put OpenMP for loop or you do SD threads, actually I got that stood threads to be actually sometimes faster. The problem is that you don't have hooks to pin a thread to a core or to pin thread to a NUMA region in this standard. And this is why other libraries like HPX or other things can help you do that. And OpenMP does it using environment variables, which is horrible API, but still it allows you to do it.
Yeah. So the problem is there's no portable way to specify that. And that's why it's not in the standard. And if you really care about the performance, you usually care about the performance on one of the specific computers up there. Not all of them, but one of them. And then you have to tweak machine-specific code, and we're still not there that we go to fairyland where we have compilers and infrastructure that will write the best performing code regardless what kind of hardware from a single source. That might be a goal in the future, but it takes a lot of work to get there, and we're not there yet. Sorry. But at least you don't have to fiddle with APIs like POSIX threads anymore, which are horrible to use correctly, easy to misuse, and easy to make mistakes or forget to look for the error conditions there. And I've been there, done that, wrapped that in myself in the 90s, and it's not fun if things go wrong. And it's very easy to make things go wrong. So that's why having a memory model and some low-level facilities actually help a lot. And if you're eager, you could use existing libraries or even build your own based on these elementary building blocks. So again, whenever you use mutual exclusion, use the local lock guard variable to guard your code. It will actually, when you construct the variable, it will call the lock function on the mutex, acquire the lock, and block until it gets it. And whenever it leaves the region, it will automatically release the lock, which is very, let's say, safe way to use mutual exclusion semantics there. If you ever intend to call separate lock and unlock, it's like calling new and delete yourself. Not something you should do unless you're really an expert and know why you're doing it. Sometimes you have code that should run once for, let's say, initializing something, and there's also a standard library version is called call once that guarantees that only a single thread and only once actually the underlying function is called. And if another thread or later time the same thread tries to call once that function again, it will do just nothing. If you have mutexes or locks, you might want to synchronize a little bit more clever, not only mutual exclusion, but you might, for example, want to implement a queue for synchronizing between producer and consumer. And if you want to implement that, you should use condition variable together with the unique lock to allow you to wait for a condition. So even if you acquire the lock, you might not be able to, let's say, get something out of an empty queue, so you have to release the lock temporarily while you're waiting for something to be put in the queue by another thread. But whenever you get notified that something is in the queue, you want to wake up, reacquire the lock automatically, and continue working. That's what condition variables are for. If you couldn't follow my very quick explanation, you better go back to a course on how to write your own synchronization mechanisms and how to apply condition variables and mutexes correctly. And usually for our student, that takes at least half of a semester for them to grasp everything around that. And there are usually higher level mechanisms beyond condition variables and mutexes that you want to use without going down to the very basics. Because again, this is a mechanism that's easily to misuse. For example, whenever you're waiting on a condition variable, you need to recheck the original condition beyond that, because whenever you wake up, it might already have been invalidated already since you last checked it. Well, anybody has used condition variables in his or her life so far? Okay, those are the experts you have to ask for. The lowest level synchronization mechanism is actually atomic variables, and the C++ standard committee worked very close with C to make atomic variables work the same on both platforms and actually be able to mix code between C and C++ using these atomics. Why I don't recommend that you use C anymore. Anybody still using C? Get rid of your C compiler. Compile your code with C++. There's no means, except for very, very tiny hardware, let's say 8-bit controllers, that you do want to use C. And if you don't believe me, go back or meet me at home and I will show you or hit you hard enough that you forget about using C. C is just wrong. It's a dead language. The committee is dying off. And also, it's a language that has so many problems that are solved by C++, and it's, you just shouldn't use C anymore. But nevertheless, we can interoperate with C code in the base of atomics. We have atomics for, let's say, integer numbers, booleans, boolean flags, and we even pretend to have atomics for higher level system, but those are usually implemented by using mutual exclusion around the operations of that of a class. There is the option for implementers and hardware vendors to provide log-free atomic operations, and if implemented correctly and you use them correctly, you might use them to implement fast, let's say, log-free data structures, but that's a kind of a magic, and my wizardry skills don't go onto that level of magic to actually be able to do that my own, and I'm a little bit afraid of these log-free data structures because in theory they might work, but in practice you might just make an implementation mistake when doing so, and that's any kind of concurrency problems are very hard to actually test for. Once you know what's wrong, you might be able to write a test case to show that it's wrong. But if you don't know that something is wrong, it might be very hard to get to the timing setup right that you can show that things are broken. And yes? Go ahead. Give it.
Yeah, what's the status of the current log-free data structure implementations? Is there going to be a standard, for example, log-free heap implementation for the standard library, or?
I didn't, maybe Mauro knows better, but I didn't attend SG1 the last two meetings, so there might have been papers around for standardizing log-free, whatever structures we get, but I haven't seen it consciously.
I had the impression, I actually made a comment at the meeting at some point, that log-free data structures depends usually on what you want to do, so they're not completely generic. It's difficult to create a standard library container which is log-free. It depends what you're doing. There are also other proposals for having more like system-like data structures, like readers and writers, things like this. They're very interesting ideas. Just it's not clear who's going to use those data structures, and so who's going to use them? It will be operating system people, and but it's very hard to have general algorithms that works on them, and so I don't know
Well, there's SG14, which is about low latency, and they might provide some data structures around that, like bounded queues, for example, that are somehow synchronized, maybe. But I'm not sure they will get there, or when we will get that. It's not something you will get definitely for C++17, for example. But that's a good thing. You can invent your own and propose it for standardization if you have users. So, there's one thing where I believe it's something that was done in the wrong way, but it was done before I joined the standard committee. So, you can have thread local global variables. I regret that this isn't implemented via the standard library, but as a language feature. And the reason it is a language feature, so a kind of what's called a storage class, like static or external, what you can write thread local in front of a global variable. It must not be one that is local to a function. Then that you get each thread that you spawn will get a copy of that variable for itself, and so you don't, if you access or mutate that variable, each thread has its own version to use. So, in my opinion, this should be actually done via a standard library class, but it isn't, so that's why we have these thread local global variables, which are not as bad as other global variables because each thread gets its own copy. You don't have any kind of concurrency issues, but they are still more or less global, so you better put them as, let's say, static members in a class and manage that their contents around the class with the class API. The thing is, they have this C++ lifetime guarantee, so whenever a thread ends, the lifetime of a thread local variable also ends. And this is one thing that might make spawning and joining a thread very expensive. Let's say you have thousands of thread local variables. Whenever you spawn a thread, all these 1,000 thread local variables have to be initialized for that specific thread and also destroyed for that specific thread. And if the initialization and destroying costs you some effort, that's a lot of code to be run at thread spawning and thread joining. And that's why thread locals have to be used carefully, or at least with a grain of salt, or it's not something you should take as a free to use resource. So that's where we are waiting for having things like thread pools, where actually a thread pool wouldn't require to start threads over and over again, but reuse threads started, so you don't get the lifetime things. But on the other hand, you might have a task that's run partially on one thread and then switched over by the thread pool to another thread, and it will not retain its thread local variable values because it's now on another thread. So we again need something that is task local, so you can have, let's say, a local state that keeps alive while things go on, and again, that is not easily available. And that's more or less what I wanted to show you. I have some more slides on move semantics, but I told a lot about that yesterday. And maybe to finish up, just some advertisement. There's a question there. Let me just finish with that slide. We provide more training, and again, what might be interesting for some of you is we also do things like code reviews, architectural reviews. So whenever you come up with something, or something where do we stand? Do we do good software engineering? Have we good C++ code? How can we improve that? We might not be able to find all your bugs, but we might be able to help you to write code that is less bug prone. And again, forget about C and apply C++. And if you need anything, I have another final slide, but that's more or less the aerial view of our campus, except that these 3 barracks you see in the front are now replaced by a new building that we move into in January with our offices. And it's about 30 seconds from lecture to swimming if you intend to do that in summer, which is
Or
quite nice.
Or to suicide if you want to jump into the lake.
It's not that deep there. You can stand at the So there's a great.
I have a question for these thread local variables. Does it
Yeah.
mean that, for example, if I use a library that uses such thread local variables,
Yeah.
that every time that I, in my code, create a new thread, I am basically paying for some initialization under the hood?
Exactly.
Okay, so a library shouldn't use
It's
such things.
heavily depends on the, let's say, implementation strategy and what types you put in the thread local variables. If it's just a thread local int, it might not be initialized at all. If it's initialized, it might be zero initialized, and that's typically quite cheap. But if you have, let's say, a thread local with the class with the, let's say, highly involved construction going on, maybe creating stuff on the heap while it's constructed, that might be quite expensive on that. So be careful with that. But it's not that much different if you use thread locals in the past. You use POSIX system calls to do so, and there you usually had a pointer, and if you wanted to initialize that pointer beyond the null pointer, you would do more than just setting some bits to 0, but you would actually call out to malloc and allocate something or let that point to somewhere else, and that would be involved as well. Maybe what could be a useful thing for thread locals in a library, for example, is if you do want dynamic data structures to be used within a thread, it can be beneficial to have a thread local memory pool. That way, when allocating or releasing your stand-on, you don't have to acquire a mutex, which would be required at least when releasing memory from the global memory pool. For example, the GCC malloc library underneath, which is underneath new and delete, would do thread local allocations and have already thread local pools. But when you delete that, because it cannot guarantee that the pointer comes from the current threads pool, it needs to acquire a mutex to sort it out where it belongs to. So that's something under the hood. At least the last time I looked, maybe it changed today, but that's so for memory pools, we created a framework in the 90s that's still in use. We have thread local memory pools for dynamic data, and that's helps, especially with the thread pool where you don't release the thread and create new threads over and over. Yeah, final questions? We are running out of time.
Okay, I'll try to keep it short. Thanks for your presentations. I really liked all your controversial comments, like we should throw away the C compiler. I assume you think the same for Fortran compilers.
That's even worse.
Even worse. That's what I expected. Unfortunately, we have to work with the codes which our users are running on our machines, so that's not a viable option. But besides that, I really appreciated your controversial comments. My question is, you gave us a lot of do's and don'ts. Don't use naked pointers anymore, et cetera, et cetera, et cetera. And this is really valuable for me personally. Where can I go to find the proper C++ programming book now? If data design patterns is now way out of date and contains really bad code, I want to know how the do's and don'ts of programming in C++ 11 and C++ 14. What is that for dummies? So what is the book I'm supposed to get?
A couple of years ago, I had a sabbatical and started to write a book. Unfortunately, halfway into that sabbatical, I got a slip disc on my back and I couldn't work for the rest of the sabbatical, and that's why the book is more or less half done. But you can read parts of that. If you go to my lecture sites, each week there's a self-study column in a table where there are parts of the book, and if you send me an email and want to get the most current draft of what I've got, I can send that to you. But most of the stuff that I told you about templates and so on is not written down in a way that's digestible yet by users. But a lot of things, an overview of the algorithms, how to apply functors and stuff like that, that's already written down. There are books on the market who look for pieces, but the overall textbook approach, a lot of C++ textbooks, as I teach C++, I have shelf space, several meters of C++ books on my shelves. Many of those have been written after the model of Niklaus Wirth's Pascal user manual and report. That was never intended to be a textbook, but starts out how the language is actually parsed. And many programming books follow that very successful book schema by explaining how a language by how the compiler works, which is a very bad way to learn to program. That's the model everybody copies from everybody else. So I deliberately didn't do that. On the other hand, I expect some programming experience. So my book will never be able to read as a first programming textbook, because that's also not my audience at our university. We teach practitioners, they have a 4 years apprenticeship in application programming, most of them. So we expect them to know how to program in some language already. Bjarne Strustrup has 2 books, one for very beginners and one the programming language. But again, both are the C++ programming language is not really a book teaching about good style. It teaches about what's available, and also it teaches a lot of things I consider you should no longer do, like using plain pointers. So first example, write your own vector, and that's the last class you want to write yourself.
Since you mentioned Strustrup, it's worth saying that the C++ core guidelines that Strustrup
That's
and
something
Sata
new,
recently
yes.
produced, it's like a web article which contains all of the condensed knowledge and best practices of some of the C++ gurus out there, and it's full of lots and lots of really useful little things like that. Don't do this, and then it shows you an example of what you should do instead. And it's not a finished document. It's a kind of work in progress which is continually being added to, but if you Google the C++ core guidelines, a couple of afternoons reading through that will really, improve your skills.
Yeah, the core guidelines is work in progress and relatively new. And again, there are some things I consider controversial because they still use plain pointers to mark non-owned data. And I believe that they have a kind of a wrapper for I own this pointer. It's called owner, and it's just an alias for the plain pointer. But there's also there should also be a non-owner or it's hard to find a good name to mark all the pointers that you don't own. So you can actually, if you have still plain pointers in your code, you see that's old code, I have to think about it. And there are things like array view and string view, and especially the array view is not the one we want to standardize, at least not the one Mauro wants to standardize, because it's too primitive for let's say, multidimensional arrays. It's just for getting rid of the pointer size APIs of C, where you lose the dimension of an array. So the problem is it also depends. C++ is such a versatile language. It depends on your skill level and your domain and the constraints surrounding you, what parts of the language are good for you to use. And that's why there isn't a single book out there yet, and there are too many different opinions because we all have different, let's say, parts of the overall set of domains where we say, okay, in this part, that's good. In some other part, that might be some overlap. Other things are also good that, on the other hand, you don't consider good. So it heavily depends on the skill level. So if you're a standard library implementer, you better know how to use pointers. But if you're a standard library user, you better avoid pointers. So sorry for that. It's just too big to have a good... If I find, let's say, another time for a sabbatical, I might finish my book. But I'm too busy in going out and telling other people how to use C++ properly, like today. Well, you can have a glimpse, and any feedback that you get is give me is fine. And I'm really eager to look at other people's code and help them to improve it.
And another way is to Google the question and go to stackoverflow.com to see the answers. And
But even there, sometimes you have to pick the answers with a grain of salt.
Oh yeah, you need to look at a couple of answers, but you know, at the end you get quite a good sense of what's going on.
And as a last resort, send Mauro and me an email.
Yeah, and I will forward to him.
Okay, I
Okay.
think we're done for
Yeah.
me at least now, and
I would
hand
like
over
to thank
Mauro.
Peter for being here.
Thank you
I
for
hope
paying
you
attention.
find useful.
Do you have a list of the attendees later on for me to?
I can get it.
Yeah, or otherwise, feel free to send me an email if you have a question or want some resource that I didn't put up on the wiki or cannot find anything. You should be able to find me easily. My name is quite unique in spelling, so I show up quite quickly on the hit list. You might even feel lucky with Google to get me. Thank you.
All right.
Enjoy your lunch.